Good afternoon, everyone. Thank you for coming to this PhD seminar. Today, Kamran will present his research on untitled programming. So, I'll leave the floor.
Hi everyone, I'm Mohammad Kamran Khan, first year PhD student in Libris, and today I'm going to present my work on ASP-based framework for operating room scheduling with beds management. So the outline for our today's discussion will be, I will have some basic motivation on the problem, give some introduction, and then about answer set programming, some experiments made, the preliminary results we got, and conclusion in the end. So, for any country in the world, the health sector is one of the important pillars for that country. Inside the health sector, there are hospitals which are the main component of those health sector because they are always under constraints in terms of budget and human resource. They have limited budget and they have limited human resource. Within any hospital, then the operating rooms are the most important section or unit. We call the operating rooms as the heart of the hospital because it is the only important section where a lot of things is going. It's not just a patient inside the operating room, but there is a lot of process going on inside a surgery. So the hospital managers, they want to reduce the cost on one side and they want to maximize patient satisfaction on the other side. So it's like they want to decide what to do because cost for the human resource, the technical resource, and the material resource, the cost is involved, and on the other side, the patient satisfaction because the patients need quality care. They need to be they need to be operated within time. So the operating room is the largest cost and revenue center. It almost consumes 33% of the hospital revenue budget. According to a survey by the National Health Centre Service England, the NHS hospitals could carry out 291,000 more non-emergency operations if they organize the operating room schedules. Long waiting lists are among the most heard complaints in general healthcare. There are always long waiting lists. So in modern hospital, if you go to the hospital, then there are always very large surgical waiting lists. Thousands and thousands of patients are waiting for their surgeries to be done, and which is caused basically by the inefficiencies in the operating room planning. So that motivates us to have an efficient operating room schedule for a particular problem to deal the waiting times of the surgical patients and try to minimize as much as possible the waiting time for the surgical patients. So, operating room scheduling problem, as the literature suggests, is a task of assigning patients to the operating room. So, we are going to assign patients to the operating room, but also taking into account their surgery durations, the priorities, the shift durations of the operating rooms, and the availability of the beds for the entire length of stay. Because a patient cannot be transferred to the ward without having bed for that patients. So there must be some bed management as well. Apart from the surgery, from the patient in the operating room, there must be some beds management for that particular case. Given that patients may have priorities, because there are patients with high priorities and low priorities, some patients are elderly patients, they have to be treated before, so there are priority system, and we have to accommodate the high priority and then the low priority and then the others if the space is available, but we have to take into account the bed management. Recently, complex problems that involves optimization like ORS problem are usually the target application of the answer set programming, and it is a declarative programming paradigm developed in the field of non-monotonic reasoning and logic programming, so it's a type of logic programming. ASP has been successfully used in several areas like AI, bioinformatics, hydroinformatics, and recently for industrial applications. The general syntax of AI, as all logic programming languages, has rules and constraints. So a rule is something that has a body and it has a head. So the head is true if the body is true. And then there are constraints and some weak constraints for that particular case. And in ASP, it is in a very rich and syntax form. The implementation is very easy in the sense that you can easily understand, easily model the problem in your logic program. The solving process of ASP is very important. Since first the problem, whatever the concrete problem is, needs to be represented in a form of logic program. Just like for traditional programming, we try to program the problem. In logic program, we model the program. So we have to model the logic program, the problem in a form of logic program. So this part, basically the problem, and this, the logic program, basically the computer going to execute this problem. And this logic program consists of two parts. The first part for that program is the problem data model. What are the facts about the problem? What is known about the problem? What we know about this problem? And the second part is the problem class, which we call encoding, that takes those inputs and try to reason with those inputs to produce a logical output. The logic program is then given to the ASP solver, and these solver internally they try to then evaluate those inputs and try to produce some optimal solutions. So the logic program is passed to the ASP solvers. In this case, we have a claim book. It is basically ASP solver. For answer set programming, is a computationally very fast solver. And the partial or complete sets of solutions, in case of optimization problem, the best solution is found. So optimization can also be dealt with this ASP paradigm. The methodology for ASP is three types. It takes 3 steps. It first guesses all possible solutions. So all possible solution candidates, it guesses all the possible solutions for a particular problem, because a combinatorial problem always have a very large search space. Then it tries to check admissible ones, those which are allowed in that model. So that by using some constraints, using strong constraints, it tries to cancel out or false to those models which are not allowed. And then the third is for optimization. If you want to find an optimized solution, and then we use weak constraint, in which there is some type of optimization to deal this problem. So, as I said, the problem needs to be first modeled, and that model needs some inputs. So, looking at the logic programming paradigm, it is not a type of programming paradigm where the control is in the hands of the programmer. Because in traditional programming, the programmer programs the problem with a form of control flow. The total execution of the problem is in the hands of the programmer. But here, in logic programming, you have to model the program as much as you can. As much information you have, you just try to give the particular information for that particular problem. And then you should have an encoding that reason on that based on those data models, or you call it facts, and come up with some solutions. So, as I said, the waiting list, we have thousands and thousands of patients. We take the subset of registrations from that waiting list. And those registrations consist not only just one patient. It consists of list of patients. So this registration basically is like a table consists thousands, or in our case, we took, by the way, in Italian health system, they only plan for 5 days. So it's a standard. They plan for 5 days, and like it was a normal question that how they're playing for 5 days, so it's standard in the papers, and also that you have to have a schedule, pre-schedule for 5 days of the next supporting week. So because operating rooms are always under different types of scenarios. The patient doesn't come on time, there are a lot of things that happen, so the 5-day schedule period is recommended. Okay, so as far as the registration is concerned, a patient should have a registration ID, priority of the patient, it's high priority, low priority, the surgery duration for that particular patient, what's the surgery duration that is going to be, the length of stay, the entire length of stay of the patient from admitting into the OR all the way to the ward. So it's the complete length of stay, we say duration of stay for that particular patient. The ICU, like if a patient is shifted to ICU after operation, it's a critical situation. And then we have specialty and an advanced parameter that shows if a patient comes 1 day before, if we try to program, because some patients, they are supposed to come a day before the operation, and others, they can come on the same day. So we have this advanced parameter that some patient can come a day before and others, so it's like different cases. Okay, so this atom registration RPS, this is a complete atom for registration predicate, and it includes all these parameters for a particular patient. Next in the data model needs to be considered is a master surgical schedule. It is a surgical schedule that is prepared by the hospital authorities for assigning ORs to a particular specialty. Because the surgical schedule is a type, as you can see, these are ORs, total of 10 operating rooms and 5 specialties. These 5 specialties include general surgery, child surgery, orthopedic, urology, and gynecology. So 5 specialties were considered. Specialty 1 is for general surgery, then 2 is for child surgery, specialty 3 is for orthopedic, 4 is for urology, and 5 is for gynecology. And for every specialty, they have dedicated operating rooms. So 3 operating rooms for specialty 1, 2 for specialty 2, 2 for specialty 3, 1 for specialty 4 because it's urology, so they have dedicated 1 operating room for that particular specialty, and 2 for the orthopedics, so gynecology. So and then they have scheduled for every day 2 shifts in the morning and evening, and for every shift they have the same operating room for that particular specialty. So it's like for 5 days they know that which particular OR is allotted to which particular specialty. Further, this specialty has been linked to the wards. So for specialty 1, there is ward for general surgery with some number of available beds. For specialty 2, there are some wards for specialty 2 with available beds, and 3, 4, 5. So they have linked like the specialty with the wards. This is also these instances shows to link each OR to a session for each specialty and planning day as established by the hospital master surgical schedule. So the OR session, which you call OR shift or OR session, is a shift in which it's a complete shift of 5 hours, so 300 minutes. It's a complete shift. For morning is 5 hours, for evening is 5 hours. So it's 2 shifts, and within those shifts, we have to schedule the surgeries. The surgeries should not increase the surgery schedule. Like the maximum allowed surgery duration, the surgery should not increase. The output of this is stored in atom X. That shows that for a particular registration of priority, is assigned to an operating room for a session in that day. So it basically assigns a patient with a particular priority, P1, P2 or P3, to a particular OR. In this case we have 5 specialties, so it depends on which specialty the registration belongs, and the session end date. So as I said, every specialty is associated to a ward. So each specialty has a ward, and every specialty has number, like 1, 2, 3, 4, 5. So for every specialty there is a particular ward, and inside those wards, please remember, they have available beds. So instances of beds is we have specialty linked to the ward, the available beds in those wards at that particular day. How many available beds are available on that particular day? So all this data model basically includes the facts, the data model for our procedure. And if we look at this length of stay timeline for a particular registration, by registration I mean to say a particular patient. So as I said, we have an advance parameter that shows that a patient can come a day before the op day. Then there is a surgery for the patient. After the surgery, the patient, if necessary, can be shifted to the ICU. If not, the patient will go straight to the ward, and after staying in the ward, it will be discharged. So this is a complete length of stay, duration of a particular journey of a patient from admission to the discharge. So the main point here is that if a patient has been done with the surgery, it can either go to the ICU or not. Depends on the condition of the patient. And this timeline is for number of days. For each day, for each patient, there can be this. So the objective function of this particular optimization problem is to assign as much as possible the registration from the waiting list subject to sum of assigned registration duration may not exceed the session duration. The shift duration should not have maximum amount of surgeries than the shift, because then it becomes overtime. So we have to take this into account, that we have to assign only those surgery durations which are within the shift duration. All P1s registration must be assigned priority for P1s, and then P2 and P3, because P1s are a priority. They are a priority patients, so we are interested for all P1s to be assigned. And then there is a minimization for P2s over P3. Respect the master surgical schedule as provided by the hospital for a particular specialty assigned to a particular OR. So it should not be violated that you are assigning a specialty 1 patient to an OR 4, for example, because it's not allocated for that particular patient as per the master surgical schedule. And there is available bed for the entire length of stay in the ward, either before surgery, and ICU and ward after surgery. So ICU is a particular type of ward where patients from any specialty can come. So it's like one ICU for all specialties. So it's generic ward, but the percentage of patients coming to the ICU is very less. So having the data model needs to have an encoding to reason with the model. In the first rule, basically we take the registration and we take those terms which are of importance together with the master surgical schedule for the 5 days, and we try to reason what can you give for a particular registration of priority and operating system for a session in a day. What is there? So it basically guesses all the possible solutions, all the possible combinations, taking into account the registration and priority and MSS. So it's a huge search space, all the possible solutions, and it guesses this by having this registration atom and the master surgical schedule. Rule 2 and 3 are basically constraints on this search space, that the same registration should not be assigned more than one in different OR or session. If a registration is assigned in the morning, it should not be assigned in the evening. And if a registration is assigned in the morning in one OR, it should not be assigned in another OR. So these are these constraints. And these constraints are given by these two rules. Then there is surgery requirement, that the total length of the surgery duration assigned to a shift or session is less than or equal to the session duration. That the assigned surgery duration should not exceed the session duration. It must be taken into account. It must not be violated. So the last rules basically show the minimization requirement of registration with priority 1. So we want all P1s to be assigned, and registration R with priority 1 basically shows a registration with priority 1 should be counted, and it should be checked with the total number of P1s, and if that is greater than 0, it is not possible. It should not be allowed. Assign all of them. So it's an integrity constraint, a strong constraint that must be taken into account. And then we have weak constraints for P2s or P3s. That if the space is there, assign P2s and then P3s for that particular registration. Then, after assigning the patients to the wards, to the operating rooms, it must also be taken into account that there are beds available. So, as I said, there must be a bed management part, and this bed management part is basically an extension of the OR problem already being done by the research here. So this bed management part is an extension of the ORS problem. To assign a bed in the ward to each registration for the days before the surgery. There are some patients that are programmed a day before. So for them, there must be a ward bed for their stay before till the length of stay. So this rule basically tries to accomplish that. Rule 10 and 11 tries to accomplish the other two conditions, that if a patient from the operating room goes either to ICU, so there must be a bed in the ICU, or assigns a bed in the ward for the period after the patient was dismissed from ICU and transferred to ward, because no one is going to stay in the ICU for, it's very terrible. So they have to be shifted to the wards. It must also be taken into account by this constraint that the number of patients occupying bed for each day is never greater than available beds. So if there are available beds, it should not be the case that the number of patient occupying the bed should be greater than the available beds. And similarly, the number of patients occupying a bed in the ICU should never be greater than the available bed in the ICU. This is our methodology. So for this, we have a Python registration generator that generates all the parameters for this particular ORS problems in a form of facts, and then we have ORS encoding. We give the facts together with this encoding to Klingo. Klingo generates results, some possible solutions, and those solutions are then analyzed again by an interpreter or by Python. The experimental setting of our ORS problem is for 5 days, planning period of 5 days, and randomly generated 350 registrations with available beds, 10 ORS, 5 specialties, 5 hours long morning and afternoon sessions, 2 shifts with 5 hours, and 60-second execution time is given for this particular problem. Klingo as ASP solver. So the analysis focused is on efficiency with respect to OR time and beds occupation. OR time efficiency is the ratio between the total time occupied by the assigned registration to the total OR time available. And bed occupation efficiency is the ratio between the beds occupied after the planning to the available ones before the planning. So these two efficiency parameters needs to be considered: OR time efficiency and bed occupation efficiency. These are the parameter input for the registration generator for 5 specialties with different randomly generated registration and 10 operating rooms. There are some surgery durations, length of stay, ICU, percentage, length of stay for ICU, and length of stay before the surgery. For some patients, if they come in advance, so we set that to 1. So this is the registration parameters for the input generator. The beds, we created 2 scenarios. In one scenario, scenario A, we have abundance of beds. The beds are in abundance. As you can see, we have 5 specialties, and for 5 days, for each day, for example, specialty 1 has 80 available beds. So abundance of beds. And for the second scenario, we decrease the number of available beds. So the bed number is the limiting factor in the second scenario. The results we achieved from Klingo is that we have 10 instances, and all these 10 instances are from the registration generator. We can see 3 priorities, P1, P2, P3. Total number of registration generated 350. Out of 350 generated, 266 were assigned to the ORs, and all P1s are assigned. Priority for P1 has been kept. So for all these 10 instances, all the registrations are assigned, and we can see that in terms of scenario A, in which OR time efficiency is the limiting factor, it has almost 95% of OR time efficiency. So in this case, we see that we have good results for scenario A. For scenario B, where bed occupation efficiency is the main parameter. Priority 1, 2, 3, you have total of 350 registrations. Out of that, 181 are assigned, because now we decrease the number of available beds. So at the same time, the assignment will be decreased. And all these 10 instances are generated with the same facts. Like the same facts are taken, and they are being tested for 10 times in order to ensure to have an average value, to see that there is no kind of variation in the different instances. So these 10 instances were randomly checked, and bed occupation efficiency is almost greater than 90%. These results shows the graph for just one instance of specialty 1 for 5 days. So Monday, it's like for 5 days, this graph shows the abundance of bed and this graph shows the scarcity of bed. As here we have abundance of beds, so the plot to the left corresponds to the first instance of scenario A, and to the right the first instance of scenario B. Further, to check this scheduling, we need to have a scalability analysis on the performance of the employed ASP solver and encoding for the scheduling problem. So in order to test the scalability analysis, other than 5 days planning period, we plan to scale it, and we created 7 benchmarks, 7 different benchmarks for benchmark of 1 day, 2 day, 3, 5, 7, 10 and 15 days with different dimensions. Again, the scenarios were kept the same for abundance and the scarcity of beds. We check the scalability of our encoding, how much days it can plan, how much days it can schedule. The experimental setting, so take 7 benchmarks with different working days, and for every benchmark 2 scenarios. Every benchmark was tested 10 times with different randomly generated inputs. The same ORs, 10 ORs with unevenly distributed among 5 specialties. This morning and evening sessions were kept the same, but the benchmark registrations were increased to 70, 140, 250, 350, 490, 700 and 1050. So the registrations were increased. Again, this table is not this table has been created by having, if you see, day 1, 2, 3, 4, 5, these days for every day. In order to get this reading, you have to run it 10 times, take the average of that value, and then mention it as an entry to this scalability. So every benchmark is tested 10 times in order to get an average and then to be taken into account. Again, for scenario 1, we have a good scalability of for 10 days it's giving more than 80%, except for greater than 10 days it decreases. For the second scenario, again we took the same benchmarks with the same parameters, and the bed occupation increased to almost greater than 90% with a scalability of 15 days with bed management. So, like if the beds are in scarce, still the solver tries to assign maximum patients, taking into account the beds availability. And almost to 15 days planning period is quite good, like in terms of planning in hospital scenarios, it's a good, you can say it's a good way to proceed. So normally, because majority of the research being done is only for planning period of 5 days. So because they have computational complexities of solving these combinatorial problems and having mathematical programming, so our solver try to accomplish this in a limiting time of like almost 60 seconds. So the conclusion is that operating room scheduling problem can be designed in a form of as an answer set programming solution, and we present results of the experimental analysis on the benchmark inspired by the real data from the hospitals of a small to medium Italian hospital, their requirements as per their requirements, and try to see the scheduling for a particular planning period of 5 days. Our OR solution is able to utilize efficiently whichever resource is more constrained, being either the OR time efficiency or the bed efficiency. Thank you.
Any questions?
Can you also specify
For maximizing?
Cost function or something.
Yeah, basically the goal of the problem was to assign as much as possible the patients to the operating rooms, taking into taking into account the beds availability. So to maximize the patient assignment in the operating rooms.
This is just the best solution in some search space.
Basically, the search space is it generates all the possible solutions, but then from that search space, the invalid solutions are removed through the constraints and try to come up with a maximized solution for assigning from those particular searches that has been done.
It's not the solution or just a solution of constraints. It's more than a solution of constraints.
Yeah. The constraint basically tries to limit those models from your, it's like those which are not allowed by your model. Like the constraints are the requirements that needs to be taken into account.
In practice, you should do it online, like every day you can do 5
So,
days and then the day after.
Yeah, it's a good question. Like the schedule has to be done before the planning period. Like for the next, if you want to plan the patient for the next week, you have to plan a week before. It's not online. While the rescheduling, which we have done for like let's suppose this plan is executed for 5 days, and on day 1, some patients got they are not assigned to their particular ORs. What to do? You have to reschedule the next 3 days in order to accommodate these patients that have been dropped. So this is offline, and that is rescheduling is online. That has like during the execution of the plan.
And it's based on this.
Yeah, based on
So their scheduling must be a bit of a different algorithm, right? Because you don't want to move all the
Yes, that has to be taken into account. That the previously assigned registration should be as minimum as possible by assigning these postponed registrations, and that should be automatic. Like if they know that 3 or 4 patients has not been assigned, they are due to some reasons they didn't came on that day or their conditions are not good, so they must reschedule them in the next 3 days rather than sending them to the end of the queue. So it's like an automatic.
I'd say that this is a good solution, but this is every solution has some disadvantage. Like if your system get mistakenly or server is down, what is the backup plan for your system for this system?
Actually, these type of schedules are basically given for a particular department, right? If they have a particular like anything happens in the worst case scenario, anything can happen, right? But sometimes like they have some backups for a particular thing to happen. It's like
because this is the emergency thing that someone is in ICU and some other patient is in ICU, but at that time your system get down or your server get down, and at that condition what will be?
So then they have to contact the server administrator because the particular schedule is running, and if it's a technical mistake for the server, then that's a technical, and if it's something the schedule is not working in a proper way, assigning maximum patients to a shift or assigning wrong patient to a wrong OR, then it's a schedule. But as far as this is just experimental analysis, we have to test it on real data. We are waiting for the data from the hospitals, but we are under the constraints to get that data of the patient because there are some privacy issues to get the data and then to check. So almost if it is 90% will come down to 75 to 80% of because in the original data there are a lot of problems that needs to be taken into account.
So can you show me? I'm sorry.
Sorry.
Can you show again where you maximize the so because for instance you want to allocate as much as possible.
Yes, so we try to minimize the unassigned registration. In order to minimize the unassigned registration, we maximize the assigned registration.
How we do it in the ASP program?
So with this, we try to, the last 3 rules, we try to assign the registration with P1s that are maximum, the registration with high priority, and then for the others, P2s over P3 with some weak constraint, so that the first constraint, the first rule must be achieved at any cost, and then we have these 2 weak constraints.
So you count the number.
We count the number of,
Yeah,
yes,
functionality.
totally. Yes.
Thank you for coming.